Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy, and we come back again for the lectures for the microprocessor class, and this is lecture number 28. This is part 1 of lecture 28. We will discuss in this lecture the chapter for the interrupts. First of all, we need to explain what are the interrupts and how they are working, what is the mechanism of a microprocessor to service some interrupt, what are the different types of interrupts that we have in the machine, and what are the instructions that may support the interrupts. Interrupts is one of the very important things that any commercial microprocessor should feature and should support. If you are running or if you are producing some microprocessor, you have to be able to stop the execution of any program at any given time in order to change the focus of the microprocessor to something else that may be more important or that may should draw the attention of the microprocessor to perform. So interrupt, the word interrupt means that you are stopping what you are doing and you change your focus to something else. This is in a very simple definition of the English word interrupt. So if I'm interrupting you, that means I'm forcing you to stop what you are doing, to pay attention to me, and you may go back after a very small discussion. You may go back to what you was doing, or maybe you will never come back to what you are doing. So the question here is why we need to interrupt the microprocessor. By default, the microprocessor is keep executing the program that is running on the machine through the cycle of the microprocessor, which we discussed before in the very first chapter of this course. The microprocessor, when some program is loaded into the microprocessor or loaded into the machine memory, it will keeps executing the instructions of the program one after the other through the cycle of the microprocessor. Fetch instruction, decode, execute, then go to the next instruction. It will keep doing this until one of two things happening. Either the program finish all of its instructions, or some interrupt reach to the microprocessor. So that means the microprocessor automatically is going through its conventional cycle of fetch, decode, execute for the instructions of one single program until some interrupt comes, or until the program finish, or until some interrupt comes to order the microprocessor, hey, stop what you are doing or finish this program and go execute another program. So accordingly, first of all, we need to explain the mechanism of interrupting, and then we will go into discuss the different types of interrupts in the 8086 machine, which is the machine under our investigation from the beginning of the lecture or the slides or the chapters of this lecture or this course. In order for a microprocessor to service some interrupt, I should have the code for the interrupt. So basically the interrupt is changing the focus of the microprocessor from executing what he is now performing of a program to change its focus to do something else. Microprocessor do nothing but executing programs or executing or going through some routines or functions. So in the high level language we call them functions, as we discussed before in the call and return chapter. In the high level language we call them functions. In low level language assembly we call them routines. So basically, effectively, what technically happen inside the microprocessor to be interrupted is to change its focus or change its execution from the current program to another program, or we don't call it a program, we call it a routine. And for the interrupts we call it interrupt service routine. This is actually what is shown here in slide number 2. Interrupt service routine. What's interrupt service routine? It is some subroutine that is programmed before the microprocessor start executing, and the code for this routine do exist somewhere in the main memory of the microprocessor, okay? And when I interrupt the microprocessor, that means I am giving the order to go to service the interrupt. So that's why we call it the interrupt. So in the main memory I may have some routine here, some code here inside it. We call this code interrupt service routine, ISR. ISR is a subroutine that the microprocessor should execute when it is interrupted. So to explain what actually happens in the microprocessor to service a routine, we assume that we have the microprocessor executing or performing some main program here. The microprocessor goes through its regular cycles for execution of the instructions of my main program. Okay, so I have instruction n, then instruction n plus 1, and so on. Right now, assume that some interrupt have arrived to the microprocessor. We will discuss later on, okay, types of interrupts. So assuming that I have some interrupt, maybe interrupt number 32, because the interrupts are defined through numbers. So if an interrupt 32 occurs during the execution of the instruction n here in the main program, the microprocessor will stop executing my main program at this stop the execution at the instruction n, and it will jump, will make a far jump, or we can call it a far call. In other words, we can call it a far call to the ISR, interrupt service routine, in particularly for the interrupt number 32. So microprocessor should know where actually to go into the main memory, so it will make a far call to the ISR for interrupt number 32, will execute the code for interrupt 32, and once it reach to the return function for that subroutine, okay, it will go back. So this is the service routine for interrupt 32. If he after he finish it, it will jump back where? To the next instruction in my main program. So effectively the mechanism of interrupt, okay, but this is the return to the n plus 1 instruction. So if the interrupt occurs at instruction n, that means I will return in the n plus 1. So effectively, to service the interrupt from the microprocessor point of view, it looks to the microprocessor as if it is simply a far call. Agree? So we already explained before what's a far call, and we know how a far call is working. But there are two things that we need to explain more here. Okay? The first thing that we want to explain more is how can the microprocessor know where to go into the main memory in order to, in particularly, go to the ISR related to the interrupt 32, because we don't have only interrupt 32 in the machine. We have from interrupt 0 till the number of interrupts, okay, specific number of interrupts, okay, in the machine. Okay, so how can the microprocessor know which interrupt should be executed right now? When the microprocessor receives the number 32, this actually guides him to where to go into the main memory in order to know which sub interrupt service routine to be executed. And this what we will be explaining shortly. Before we go into explain that, we need just to highlight that the interrupts in the machine have some priority. That in the previous slide we talked about the interrupt number 32, okay, and we have different interrupts in the machine. The different interrupts, okay, change or different from each other based on their priority. The highest priority interrupt ever in any microprocessor is what's called the reset interrupt. What is a reset interrupt? Reset interrupt is the interrupt that the microprocessor receive when the end user press on the reset button on the machine. So if you press on the reset, this sends an interrupt or a reset interrupt to the microprocessor, tells him, hey, we have an emergency case here. The user needs to reset, needs to shut off the machine. So, by the way, this is one of the interrupts that actually do not return. That means the microprocessor will call the interrupt service routine, the ISR, for the reset, okay, for the reset, and will never come back, and will never come back, because the order received by the microprocessor is to reset, is to switch off. Okay, that's why this interrupt has the highest priority. We also have different types of interrupts. We have what's called the internal interrupts and exceptions. We have the software interrupts. We have the non-maskable interrupts, and we have the external interrupts. Both of the non-maskable interrupts and the external interrupts are external of two flavors. So those are the external interrupts. While the internal interrupts and the software, you can call them, this is the internal ones. Okay, definitely the reset is an external as well, but it has the highest priority. That's why we put it here at the first priority of interrupts. If the priority of the interrupts is the reset, then the internal, the software, the non-maskable, and the external. The priority of the interrupts do matter for me, because if the microprocessor receive an interrupt while he is executing a higher priority interrupt, it will never respond to the lower priority interrupt. So that's why the interrupts should be prioritized. Type. So we will talk in more details about the hardware interrupts. So let us go to the more thing that needs our attention and explain how the microprocessor actually deal with the interrupts. First of all, for the 8086 machine that we are studying from the beginning of this course, this machine can recognize 256 different interrupts. The total number of interrupts for the machine are 256. Definitely, this number is way bigger than what is needed inside any machine. Those interrupts are divided into 4 groups. As we mentioned, we have the hardware interrupts, non-maskable interrupts, software interrupts, internal interrupts, and reset interrupts. In order for the microprocessor to receive any of those interrupts, the microprocessor is responding to the interrupt based on some pin, based on some pin on the microprocessor chip. So I have the microprocessor chip. The microprocessor chips have different pins, and what is mentioned here in this slide is the pin that is responsible for each of the 5 types of interrupts that we are studying here. Okay, so that means we have a pin called NMI, a pin called INTR, a pin called reset, and a pin called test. Okay, signal and test for the internal interrupts. The software interrupts are not done in hardware, they are done through the software. So accordingly, the interrupts are activated or have been called through an instruction, not a pin. Okay, this instruction called the int instruction. So int space n, this is the how the instruction, the prototype of the instruction, or how the instruction should be written. Okay, so int space n, and in n here you define the type of the interrupt, as we will see shortly in the following slides. So again, so this is the picture of the microprocessor chip, the 8086 machine, and we can here recognize the reset pin, the test pin for external interrupts, internal interrupts, the INT interrupt. We have also here the non-maskable this is the INTR, the non-maskable interrupt pin. Those are the pins for the microprocessor to receive the different interrupts. Microprocessor is affected by the interrupts based on the status of the 2 flags in the status register. We talked about the status register extensively before, and we actually discussed each and every bit in the status register except those 2 flags. So actually we talked about the overflow flag before. The direction flag, we actually will not study it, forget about it, we actually skip it in this course. We talked about the overflow flag, the sign flag, the 0 flag, the auxiliary flag, the parity flag, the carry flag. Left for us for this machine is to talk about those 2 flags. Those 2 flags are the responsible flags for the interrupts. One of them is related to the internal interrupts and or the software interrupts, and the other is related to the external interrupts. The INT, the interrupt enable, the IF is for the hardware interrupts. The trap flag is for the software interrupts. Both those flags should be 1. Both those flags should be 1 in order for the microprocessor to respond to the interrupts. That means if those 2 flags are zeros, that means the microprocessor will neglect the interrupts, definitely, except the reset interrupt. The reset interrupt is non-maskable. It cannot, the microprocessor cannot neglect it or ignore it, even if the status flags is indicating something different. Okay, but so the default values for those flags or for those bits, IF and the TF, the default values are ones. However, if the microprocessor have went through or currently is executing some interrupt service routine, those flags should be set to 0 in order to prevent any other interrupting the microprocessor while it's executing in one of the interrupts. Yep, the first thing that the microprocessor should do once he wants to execute some interrupt is to reset those two flags to zeros. So accordingly, since we now explained the mechanism of the interrupt, we can actually go through the flow of operations or micro instructions or steps that the microprocessor should do on receiving some interrupt. So if the microprocessor receives an interrupt, the first thing, so as we mentioned, it is a far call. So first of all, he wants to save the old flags, all the flags. So actually the status register should be pushed into the stack. Okay, should be pushed into the stack to save it, because the microprocessor needs not to change the status, okay, while it is executing in the executing the interrupt service routine. But the status register should be pushed into the stack. Also, he have to clear or reset, mean the two flags here, to prevent any other prevent other lower priority interrupt prevent other lower priority interrupts from execution during interrupt service routine execution. Okay, agree? Now then, after doing this, then what else that the microprocessor should do? It should push the old CS and IP should be pushed where? Into the stack. Okay, maybe I will return back from the interrupt service routine, but this is definitely will not happen in the reset case. Then a new value for CS and IP should be calculated. We will indicate, or we will show exactly how this calculation is being done in order for the microprocessor to do the far jump or the far call that we have just explained. Okay, then the program execution will resume at the interrupt service routine. Interrupt service routine. So here okay, interrupt service routine will be will executed after pushing the status register, all the CS and IP into the flag into the stack and clearing the flags. Type. Now, how can the microprocessor know, assuming that the microprocessor have received an interrupt number 50? How can the microprocessor know where to go from that number? All what the microprocessor will receive is the number of the interrupt, the ID for the interrupt 50. What will be happening? Okay, so in order to assist the microprocessor to do that, we have what's called the address pointer table. What's the address pointer table? This is a small ROM, okay, small memory. This is a small memory do exist inside the machine. In that memory, okay, it's not a ROM, it is actually a RAM. Okay, so in that memory, the values for the CS and the IP for each interrupt is being stored in the APT. So APT stands for address pointer table. Address pointer table. So the address pointer table carry what? Carry the full address, segment, and offset values for all the interrupt service routines of all the interrupts of the machine. If our machine here has a total of 256 interrupts, as we just indicate, interrupts, that means I need 256 bytes multiplied by 4, because actually in each address or for each interrupt I need 4 bytes. يبقى those are 4 bytes. 2 bytes for the segment and 2 bytes for the offset. The total is 4 bytes. So 4 bytes multiplied by 256 interrupts, that means I need 1K, okay, which is 1K memory, 1K memory to store the addresses for the interrupts. 1K memory have address of how many bits? Okay, exactly 10 bits. So these are the 10 bits that are shown here. Okay, so 10 bits means 2 hexa digits plus 2 bits. So the addresses on the address pointer table starts from 00 in hexa, 000 in hexa, okay, 000 in hexa, 3 zeros, okay, in hexa, till cam, till EF3 in hexa, okay, or FFF in hexa. Okay, this is actually the values that we can have for the address. Type. Now, if I'm receiving interrupt number 50, those addresses are chronologically or in order. That means the 4 bytes here, the first 4 bytes here are for interrupt number 0. The second 4 bytes are for interrupt number 1, and so on. So accordingly, the first vector here, we call it vector. The combination between segment and offset, we call it vector. Okay, so for vector 0 or interrupt 0, okay, I have 4 bytes. 2 bytes for the IP, followed by 2 bytes for the CS. Okay, those total 4 bytes are storing the address, offset, and segment for interrupt number 0. So for the next vector or vector 1, then the second one, and so on. Okay, so this is how the microprocessor maps the interrupt ID, okay, to a location where it has to go into the APT in order to get the addresses for a specific interrupt. Okay, now the microprocessor has a guidance where to go into that table in order to grab the segment and offset in order to make his far jump. Okay, so accordingly, in order to understand what's going on here, assuming that the microprocessor received interrupt number 50, okay, so for interrupt number 50, where are the locations in the ATP that the microprocessor should go in order to grab the addresses for interrupt number 50. Can you do this calculation? So interrupt 50, okay, that means I have previous to this I have 50 different addresses. So from interrupt number 0, okay, interrupt number 0 takes 4 bytes, okay. Those 4 bytes has the addresses 0, 1, 2 and 3, okay. Interrupt number 1 takes the addresses 4, 5, 6 and 7. Interrupt number 2 will take the addresses 8, 9, 10 and 11 and so on. So can we calculate where to go for interrupt number 50? Yes, the calculation is simple. Starting at address 50, so I can actually deduct here a relationship. So the number of the interrupt multiplied by 4 will give me the starting address. يبقى 50 multiplied by 4, which is 200. طبعا here we are talking about decimal, okay. In decimal is actually the starting location for يبقى 200, 201, 202 and 203 are the locations for the interrupt service routine for interrupt number 50. The first two locations are for its IP, يبقى IP of 50, and the second two locations are for the CS of the interrupt 50, okay. So if we convert this into hexa, we can identify where into the ATP I have to go in order to grab the addresses for the interrupt number 50. I just want to make sure is this calculation is done here. Can we do this calculation? So actually the at ATP, so in ATP here I should go to the 4 locations, okay. So if we do a simple calculation here through our calculator, let me just do this calculation. Let us do the calculation. I just want to do a full demo here for you, okay. So if I talking about 200 in hexa will be C8, so in hexa actually here the location C8 in hexa and C9, CA, CB are the memory or the APT locations where I have to go, or the microprocessor will have to go to grab the IP for 50, for interrupt 50, and the CS for the interrupt 50. Agree? Make sense? Okay. Now as we mentioned, there are other types of interrupts. One of them is the software interrupt. As we mentioned, the interrupts are different from each other based on their priorities. The highest priority interrupt is the reset. Okay, that means no doubts, once the reset interrupt arrive, the microprocessor will go and execute it. The second interrupt or highest priority interrupt is the software or the internal interrupt, the software interrupt. The software interrupt uses only one instruction, which is the int instruction, or there are other instructions also that are can be used. We will discuss them at the end of the chapter. So int n. Okay, so here you specify the number of the interrupt. N here represents the interrupt number. So you can actually call the interrupt service routines for the different interrupts through the software by calling the int instruction. Okay, and this is the are the higher priority than the external software, and internal are higher priority than the external. So as we mentioned, so whenever you call this instruction, the microprocessor will just do or perform this as if it is a far call. However, it have to do, as we mentioned, many other things. So first save the flags, then it has to save the flags, then it has to clear the TF and the IF flags. Okay, then save the current CS and IP, then reads the interrupt 50 IP of 50 and the CS of 50 from the ATP APT, the address pointer table, from the locations 8C as we just mentioned and AC, and then start fetching instructions for the interrupt service routine 50. Okay, so if you ever call int 50, this actually what will happen inside the microprocessor. Okay, so since we have int as the instruction for the interrupt, inside the interrupt service routine there is the return instruction. iret is the instruction that should be used to return from a subroutine. This is the instruction that you have to use. Why this is different from the regular return? Because regular return does not consist of popping or the old flags. So the instruction is different from the regular return, because interrupt return means I have to retrieve or pop the CS, the IP should be popped, and also I have to pop the flags back. Okay, this is in case that the interrupt instruction will return. So these are actually the software interrupts. The next interrupt that we want to talk about is the external interrupt, the hardware interrupt. The hardware interrupts are two types. We have what's called the external interrupt, which has the least priority. This is the least priority interrupt out of all the interrupts in the x86 or the machine. Okay, first of all, the pin that the microprocessor is checking for this interrupt is the int pin. This is the name of the pin for that interrupt, and this is the hardware interrupt, and this interrupt is maskable. What does it mean by maskable? Maskable means that a microprocessor may ignore execution of the interrupt service routine for the external hardware interrupt. What does it mean by ignore or maskable? Means that if the microprocessor is busy doing something, he may not get the signal of the interrupt at all. When we experience this, if you as my students already, or we all of us experience that in our machines. Do you ever connect your USB flash into your machine and nothing happens? This happens to all of us because actually the types of interrupts generated when you connect some external hardware to your machine is an external hardware interrupt. That means the processor is, if it feels that he is busy doing something, he can completely ignore that interrupt. So what we can do, we just remove the UPS and USB and connect it again. Okay, so we call these type of interrupts a maskable interrupt. That means the microprocessor may ignore them completely and do not execute any interrupt service routine due to them. Okay, this is the least priority hardware interrupts. The second type of interrupts, and those are, by the way, controlled by the interrupt enable flag, so IF here. So if the IF equals to 0, that means the hardware will, or the microprocessor may ignore this interrupt completely. Okay, طيب. The next priority, definitely here you can the programmer or the user of the machine has the ability to clear or set the interrupt flag in his program. So you can manipulate this flag. يبقى IF flag can be manipulated by those two instructions. يبقى IF manipulation instructions. That means if you don't want the microprocessor to respond to the external interrupts, you can just use a clear CLI instruction to clear the IF flag. That means the microprocessor will never respond to the external interrupts. If you want to return them back, to return the flag back to its normal operation, so you can do so through the set interrupt instruction. A set and reset or clear and set, those two instructions are used to enable and disable, mean the interrupt, the external interrupts from the pin INTR. Okay, طيب. The second type of hardware interrupts, يبقى non-maskable interrupt, is also a hardware. يبقى this is the type of hardware interrupts, but it's called what? Non-maskable. Non-maskable, that means the microprocessor cannot ignore them, but it can. يبقى microprocessor cannot ignore them, but can delay them. Okay, if he is executing some higher priority interrupt, he will finish the running interrupt first and then go and execute the interrupt service routine for the non-maskable interrupts. يبقى non-maskable, mask means you put some cover, that means you hide from it. Okay, non-maskable means you cannot hide from it. يبقى microprocessor cannot ignore it, but it can delay it. يبقى cannot ignore, but it can delay. يبقى cannot be masked out with the interrupt flag. Okay, and as we mentioned, these are actually received on the NMIA input pin. These are kind of details for the non-maskable. No need for any of those information. What we know about it is good enough. So we just skip that. We already talked about the reset interrupt, which is the highest priority one. We want also to talk about some internal interrupts. What's internal interrupts? So we talked about the external, the hardware, which is the maskable, the non-maskable, the NMI, or the non-maskable interrupts. Those are the two hardwares. We talked about the reset interrupt, which is also a hardware with the highest priority. We talked about the software through the instruction. The last type of interrupts that we want to talk about is the internal interrupts, which are what are internal interrupts? Those are interrupts that happen to the microprocessor if some exception or error happen during the execution of your program. Like for instance, all the mathematical operations you have in your program, you are dividing by 0. If you divide something, okay, by 0, so do you have any value for this? Can you see any value here? Definitely no. So the microprocessor here wants to indicate to you that the last operation have not mathematically done successful. So this gives the opportunity for the programmer, for the system programmer, to give or to propagate or to convey the error that happens during the mathematical error. These are mathematical, usually mathematical errors can be reported to the end user. Okay, like what? Divide by 0, or maybe an overflow. If you have an overflow, that means you need to inform the user. So the system programmer may write in the interrupt service routine for the overflow is to show, maybe this is one option, to show some error message to the end user. Okay, so this message will be shown to the end user if the error is happening. Okay, like what? The stack overflow or any kind of an error message, okay, to show to you, okay, that indicates that you have some error in the calculation. So this category of interrupts or exceptions called the internal interrupts. By the way, the overflow interrupt is very well known, is very famous, because it's happening in the calculations very frequently. That's why they have some instruction in particular for this type of errors. Okay, this instruction is called into. So into means interrupt overflow. It's kind of a short name for the instruction int space 4. So int 4 means يبقى overflow interrupt is called or has the type or number 4. Okay, so int 4 has a short name for it, which is into. Okay, and since it is the instruction 4, or it's the interrupt number 4, the type of the interrupt is 4, so the vector here in the address pointer table can be calculated by just simply multiply 4 by 4, which give you 16. 16 in, this is in decimal, in hexa this is 0 1 0 in hexa. So that means in the ATP, in APT, I have to go to the memory locations, 0 1 0 1 1 0 2 1 0 3 1 0. Okay, to grab what? To grab the IP value for interrupt 4 and the CS value for interrupt 4. Another very important type of internal interrupts is the single step and the breakpoint. Those are very useful in program or software debugging, or software or program debugging. Okay, whoever of you already taking the lab have seen this. Our lab, microprocessor lab, have seen this extensively. Okay, what's a single step or breakpoint? In order to investigate your software, you need the ability to debug the code. Debug means to execute the program step by step. To execute the program step by step. How can you do that? By inserting or injecting an instruction called wait after each and every instruction in your code. Who is doing this? Some tool called the debugger. The debugger is some tool that takes your program and insert the wait instruction after each and every instruction in your code. After each instruction we have a wait. After each instruction we have a wait. So this fashion, after the microprocessor execute each of your instructions, okay, it will wait. It will be interrupted. The interrupt here will happen after the execution of each of your instructions. طب why interrupted? To give you the opportunity to check the registers and the memory to see what's going on inside the machine. Okay, and this give you an opportunity to investigate your code and see whether it is executed correctly or not. The concept of debugging will be much more clear when you take the lab, so whoever do not taking our lab will actually have seen this clearly, inshallah, during our lab sessions. Okay, so you will see this during our lab sessions, inshallah. Okay, so the most important thing that you have to know here is that the single step is one of the types of the internal interrupts, and there is a flag that allows this, which is the trap flag. So the trap flag, when the trap flag equals to 1, that means I'm enabling a single step execution for my program. Okay, so if the debugger have done this and intermingle or inject these wait instructions inside my code, that means my program will stop after each and every instruction execution and change the focus to the end user in order to allow him to investigate the code. So to cut the long story short, the trap flag here is responsible for the internal interrupts. So this is actually the flag that should be 1 in order to enable the internal interrupts. يبقى 1 flag for the external and 1 for the internal. Okay, طيب. So this is just talking about a little bit of the hardware for the wait and the halt instructions. Also we can just skip this. So here actually a summary of all the instructions that are related to the interrupts. So to wrap up here, we have actually 2 instructions responsible for clearing and setting for the interrupt flag. For the interrupt flag. Okay, actually to enable and disable mean the external interrupts. We have the int n instruction that you can use inside your code to actually call any of the interrupt service routines inside your code. Okay, yeah, but this first instructions are setting if to either 0 or 1. This instruction is a real instruction for the calling for the interrupt, so it actually do the following actions. It's actually storing the flag. يبقى دي it push the flags first into the stack. It reset TF and IF. It push the CS. It pushes the IP, and it make a jump according to the as we mentioned, the address pointer table, as we explained before. Okay, for n. Type one more instruction here, which is the interrupt return instruction. You can use this while you are writing the interrupt service routine. At the end of each interrupt of the interrupt service routine, you have to see this instruction to allow you to return from an interrupt. So actually this instruction is doing the opposite of the int instruction. So this instruction is kind of a far call, and this is the far return for the interrupts. Okay, INTO is for the interrupt overflow. It is equivalent to int space 4. The halt and the wait instructions are for the internal interrupts that allow you to step into your instruction by instruction in your code. So at that end we finish this chapter, and inshallah in the second part of this lecture we will discuss the input output, which is the last chapter for the course. Thank you, and see you soon in the following set of videos, inshallah.